Here is the most outrageous engine I've built so far. It's basically finished, a few small details to finish up on it before we go to the dyno. It is a big block Chevrolet. It displaces 760 cubic inches. The crankshaft stroke is 5 3/4, 5.75. The connecting rods are 8.75 long in it. It was originally going to be a naturally aspirated motor, but along the way we decided to put a blower on it. There's a lot of custom work gone into this engine. I've said for years that I don't build crate engines. Everything I build tends to be a one-off, and it's typically something that most other engine builders are not interested in doing because of the time factor involved and the real potential to not make a profit on it, because you put so many hours into every little part of the building of the engine. So I'm going to show you a few of the details on this engine. And the blower is a 1471. Currently we're about 5% overdrive on it, and I think that will get me up to about 5 or 6 pounds of boost. This engine's going to suck all the air out of that blower, so we'll find out when it goes on the dyno if I need to make a pulley change to change the boost it'll put out. Okay, so I made the oil pan down here. I took a stock pan, I cut the ends off of it, mounted it on the block, and then started welding sheet metal to it till I had an oil pan. Holds about 8 quarts. I tried to make it as close to the stock dimensions as I could to provide clearance for the cross member and ground clearance and whatnot. You can see here, because this is a fuel injected motor with a computer, I mounted LS style coil on plug, and to drive that there is a Harley crank trigger wheel which we're using for a crank position sensor, and in the back I used an MSD engine position module, or cam position sensor is what I'm using it for. I wasn't able to hold it in place with a typical distributor clamp because I had to machine all that area off to get it to drop down deep enough into the block, because this thing is so tall. And I just made this bracket on top to hold it in place. You can see all the wiring here. So that's the cam position sensor. For controlling breathing on this side, I take the air out through a fuel filter to try and keep the oil in the motor and not suck it into the engine. Up here to where there will be a vacuum drawer on top of the blower, so that's your PVC. And once you go into full throttle, you don't have a whole lot of vacuum, so it's hard to get all the air out of the motor. So then you have a conventional breather type arrangement which comes up here and just sucks the air into the blower out of this hole here. So that would be your breather. It's fuel injected. Originally it was going to be naturally aspirated, so I mounted the injectors down here into this intake manifold that I made. And when we're into a blower, we need to have fuel in the blower for cooling and lubricating, so I had to add another 8 injectors on top here. And this is sequential fuel injected, so I was able to tie the corresponding cylinder injectors together and drive it with the same input from the computer. I've been assured by AEM that the computer is capable of driving at least 2 injectors. Probably wouldn't want to put any more than that on it. And then, as you can see here, it runs conventional mechanical fuel injector fuel lines, which you have the injector mounted here, a cap on top with the O-ring inside to feed the fuel in through this fitting here, and then this plate I put on top to hold the injectors in place so they won't pop out when you actually have pressure, which they will do. If you feed fuel pressure to an injector without holding it in place. It'll blow it right out of the intake manifold. And you can see here the fuel lines. This is the mechanical fuel injection distribution block. Fuel is being fed up from the fuel pressure regulator. Fuel comes from here to here, and then from this piece here, and from, where's the other one? You got one supplying fuel from here and another one from down here. So you've got 1, 2, 3 fuel outlets. The fuel inlet will be right here. This fitting here is simply for measuring fuel pressure with a gauge. And right here, boost pressure is fed to the fuel pressure regulator, so as it goes into boost, it'll add a corresponding amount of fuel pressure to compensate for the boost. In this box here, I have a electric fuel shut-off valve essentially, which will be mounted somewhere in the fuel line so that when the engine is switched off, we can switch the fuel off like a racing engine, so the engine quits running when it runs out of fuel. It will run dry rather than just turning the ignition off. The reason I did that was, long story short, I needed, at the time I was trying to make the manifold as low as I could. So I made so much of the plenum below the runners. There's a real risk that fuel will puddle here when the engine's shut off, and you just have gasoline sitting there going stale. So I was trying with the fuel shut-off valve to prevent that from happening. It won't be 100% effective, but it was the best I was able to come up with. That there is a blow-off valve should it ever backfire, which hopefully it'll never do. You can see here where I modified the manifold by welding a plate on top, so I was able to mount the blower. That's the dipstick there, goes down into the pan. That's a Missouri starter motor, the very best I could buy. Runs really nice and cranks this big heavy crankshaft over effortlessly. This is the hat on top, provides the throttle body. That's the throttle position sensor. Around here, in addition to where the PVC function is controlled, this here will then be used for power brakes because it will be vacuum there, and this can be used for a vacuum gauge. And as I said, this fitting here, which connects to the fuel pressure regulator to provide a signal. There's a little screw, we can take that out there and put a boost gauge on there as well, so you can have both a vacuum reading and a boost reading. The throttle, because this is a street engine, when you open the throttle blades, a little bit is a lot. You've probably seen funny cars doing burnouts and they barely have, or top fuel drags, they barely have that much throttle opening to do a burnout. A gasoline engine might be up to something like that. If you go full throttle, it's making so much power that you could easily overrev the engine with the tires spinning. This is actually only functional on 2 throttle blades. You can see inside there, you can't, it's a little bit dark, but there's a screen in there that provides the air cleaner function. It's not going to keep dust out of the motor, but it will keep rocks and birds out. And this one here, hard to see, but let me grab my flashlight. It's actually, there's a plate in there welded in there so that this is not going anywhere. That's just an empty box. So it's really only 2 blades. You can better see the screen inside there now. The block itself, I raised the deck by putting in a cast iron spacer plate. This was originally a honing deck plate, torque plate. So essentially I've got aluminum from say here through the iron and then the deck of the block. So that's a lot of solid metal there. So what I tried to do was I machined into this torque plate and made a water passage in there that connects to the block so that water can flow up through the plate into the cylinder head like a conventional cylinder head would. And I put a plate on the outside which I sealed to try and keep the water in. And hopefully that will provide additional cooling to the hottest section of the cylinder head, which is around the spark plug and the exhaust port. We're not concerned about the intake side, it'll be plenty cool. The water comes out of the front of the cylinder head here and goes to a conventional thermostat housing or water neck. Additionally, I pull hot water out of the back of the cylinder head and feed it up into the bottom of the water neck. The idea is that if I take hot water out of the back of the cylinder head, hopefully more cool water is flowing through the block. So you're basically extracting heat from the back of the cylinder head before it's gone through and heated up to the front of the cylinder head. How well that works, it'll be difficult to quantify because you're not able to measure it, because the thermostat will just have the engine running at 180 degrees. I asked the customer, you only want an alternator on this, right? He goes, no, it's a street car, I want power steering and I want air conditioning. And I'm like, well, how in the world am I going to do that? Well, the only way to do it was to make it all. And so you can see here, I've made a plate to hold the AC, and I had to make the spacing just right to get all the alignment in. You can see the alternator is mounted solidly above it, and then I put idler pulleys everywhere to wrap the belt securely around each pulley so there would be no slippage. The adjustment is all controlled here by sliding this down to put tension on the belt right here. And so that should make it a nice running street car. I made custom rocker stands for it for the Jessel roller rockers. It's a hydraulic roller lifter cam. It's not a huge duration for such a big motor, but the stroke on this is so long that the feet per second travel of the pistons is going to be so high that I told the customer that the red line is at 5,500 RPM, and so I put a small cam in it to make good power all the way up to that RPM, and hopefully you won't take it over 5 because it'll be too scary to drive with that kind of power. So it's essentially ready to go to the dyno. We're driving the electronics on it with an AEM Infinity computer. AEM offers 3 basic sizes, although they have a lot of different products for 4 cylinders and different European cars, but this has the Infinity 7 computer which can run up to 10 injectors. They also have the Infinity 5, which is a more basic computer driving the ignition and fuel system, where the Infinity 7 can also manage traction control and all kinds of things that only a real race car would use. I had to wire the whole thing myself. I tried to make it as tidy as possible. You can see here, there we go. There we go. There's the wiring harness that I'm working on, trying to keep all the wires. The camera tends to do so much pickup, but you can see there's a bit of a mess back there, but that's where the computer will plug in, and I'll have a harness wrapped around it to make it look nice and clean. The wires are all connected with these connectors here that you use a heat gun to melt the solder in the metal and then shrink the plastic, so it's a nice secure connection. What's nice is you can have like 2 wires connected into 1 wire, as I've done here. So that's essentially it. Trying to think if there's anything else. Originally this engine was going to be naturally aspirated, and I had the compression ratio set up at about 10 3/4 to 1. When we went to the blower, we had to lower the compression ratio, so I've used 3 head gaskets in there. I have 2 multi-layer steel gaskets with a copper gasket sandwiched in between those 2, and copper coat on everything just to make sure. and now the compression ratio is right around 9 to 1. To compensate for the fact that the heads are raised up, I had to use 3 intake gaskets to get the spacing for the manifold itself. And the manifold, this here is aluminum, but the plate that it sits on is actually steel. I don't have a welding shop, so I wasn't able to weld aluminum. All this welding was done by a company that I brought everything to. But for the ends I used steel, which is under here. This is steel from here to here. That's why, and I was able to weld steel. I can do that. Then I bolted this plate, which you see here, onto the steel and onto the manifold itself. So this is basically a 3-piece manifold. It would be nice to just have Hogan build me a manifold, but they're around $3,000 plus. And while this is an expensive engine, I have tried to build it at a reasonable cost. The customer had more money than I have to throw at an engine, but he didn't have all the money in the world, so I tried to save him wherever I could. The block itself is an obsolete World Merlin 3 super block, which is no longer in production. That's why I say obsolete. It has a deck height of 11.625. I raised that to an even 13 inches with that spacer plate. That gave me a rod to stroke ratio which is much better. It was in the 1.5 range rather than being stuck with something like 1.3. The camshaft uses a timing chain to drive it. There isn't a gear drive, which is what I would have had to do if I used a dart block, which has a deck height of 11, I'm trying to remember what it is now, 11.2 I think, and the camshaft is raised 400 thousandths, and there isn't a timing chain that fits that arrangement. You have to run a gear drive, so now we're looking at $1,500 just to turn the camshaft, whereas I'm using a chain and I'm doing it for 50 bucks. The cylinder heads, I used Dart Pro 1 cylinder heads, so they're going to flow a ton of air. I had to do quite a bit of work to get the push rods to clear because of the angle, and I made the push rods by taking a heavy wall 3/8 diameter push rod, 2 of them, cutting them in half so that combined they had the length that I was looking for, and then I pushed them into a 1/2 inch OD diameter chromoly tube. So there's no way those push rods are ever going to bend. So I guess that's pretty much covered it. You can see the power steering pump there does stick out a ways, so the car that it's going into, which has not yet been determined, will need to be built around the motor rather than vice versa. And to give you some perspective of how big this motor is, you can see here it's sitting on feet and the pan is just barely there. So putting that on top, we're looking at essentially close to 48 inches, call it 46 inches in total height. And then the motor, valve cover to valve cover, if you take the alternator into consideration, you're looking at 38 inches wide. So this thing certainly is a behemoth. You compare that to this turbocharged small block here, which is sitting on an engine stand. Stepping back, they're almost the same height. The small block's a little bit higher because of the engine stand. And similarly, I mounted LS coils down here, so this is coil and plug as well. I wasn't necessary to use a crank position sensor on this one because I'm using a AEM engine position module, which serves both as a crank position and a cam position sensor. And you can see all the wiring. Once again, I did all the wiring myself. And this is a Banks twin turbo setup, which should make 1,000 horsepower with all the boost kicked in. And on the front here, this is an adjustable solenoid, for want of a better word. But by opening this with a knob on the dashboard, we feed boost pressure from the plenum to this, and then that ends up going to the wastegate, applying more pressure to the spring. So without any assistance from boost pressure, the wastegates will open at 8 psi. With the boost pressure, it'll probably be closer up to 15. Of course, somebody's phoning me, so I'm going to have to cut it off.